This is day 2 for the unit, day 1 for the flip class. We're going to be focusing on inverse trig ratios, and we're going to do special right triangles. So first thing we're going to look at is two different special right triangles. We'll look at the 30, 60, 90 right triangle. We'll look at the 45, 45, 90. Then second thing we'll do is some inverse trig ratios. So we'll look at inverse trig ratios for sine, cosine, and tangent. Right, and then we'll finish off with some applications. So the first type of special right triangle we're looking at is the 30, 60, 90 special right triangle. The name for the special right triangle comes from the angle measures. So we have angle 30 degrees, angle 60 degrees, and it's a right triangle, so we have a right angle, 90-degree angle. So it makes these specials at the sides all follow a pattern. Across from the 30-degree angle, call that side 1, hypotenuse is twice that, and across from the 60-degree angle, you have a side of square root 3. Right, so the pattern goes 1, 2, square root 3, across from the 30, the 90, and the 60. Right, so a more general way of writing the pattern is if we call the shortest side, which would be across from the smallest angle, x, the hypotenuse would be 2x, and then across from the 60 would always be x times square root 3. Right, so this pattern will work for any different size you make a 30, 60, 90 triangle. So if I took a different triangle, the angles were 30, 60, and 90. If I take the side across from the 30 and that was length 4, right, I know because it's a 30, 60, 90, the hypotenuse would be 8, and across from the 60 would be 4 square roots of 3. Right, or the same thing. If I had another 30, 60, 90 triangle, I knew the hypotenuse was 500. That would tell me the shortest side would have to be 250, half of that, and across from the 60 would be 250 square root 3. Right, so they always follow this pattern. They have that same ratio between the sides, and that's why they're special right triangles. So using the special right triangles, we can actually find the 3 trig functions for these angles, 30 degrees and 60 degrees, without using a calculator. So you see these values a lot on the SAT. Right, and the reason you see these a lot on the SAT and ACT is because you don't need a calculator to do this trig. You don't need to put it in degree mode and type in sine 30 or cosine 30 or tan 30. You can do all this without using a calculator, just by using our basic right triangle trig and that pattern between sides. So if we look at a 30-degree angle, right, I know sine would be opposite over hypotenuse, so that would be 1 over 2. So sine 30 is 1/2. Cosine 30, same thing, would be adjacent, square root 3 over hypotenuse 2. So it would be root 3 over 2, and then tangent would be opposite over adjacent, so that would be 1 over square root 3. Right, so I know all 3 of those values without using a calculator, just by using the basic trig ratios and patterns for the 30, 60, 90 triangle. So I can do the same thing for 60. Right, switching to the other angle, we have our properties for sines, cosines, and tangents of complementary angles. We know these are going to be equal, right, where we use the trig ratio, opposite over hypotenuse. Either way, we get root 3 over 2. Cosine 60, same thing, be 1/2. The adjacent over hypotenuse, and the tangent would be the reciprocal for tangent 30. because they're complementary angles. So that's going to be root 3 over 1, or just square root 3. Right, so all 6 of these you should know, be able to use them in problems. You won't have to use the calculator. If you see you have a word problem that involves right triangles, a 30, 60, 90 right triangle, or an angle of 30 or 60 degrees, you don't need to use a calculator to find these trig ratios. You should know them already from this these relationships with the special right triangles. So the other special right triangle is the isosceles right triangle, the 45, 45, 90. Again, those numbers refer to the angle measures. So we have two angles of 45 degrees, and the third angle is a right angle, makes it a right triangle. So these two congruent angles in isosceles triangle, these are called base angles. Right, whenever we have two base angles congruent, we know we have an isosceles triangle, means the two opposite sides will also be congruent. So if we label one of these sides 1, the other side would have to be 1 since it's an isosceles triangle. And you use Pythagorean theorem and see the third side would have to be square root 2. Right, and same thing as the 30, 60, 90. This is a general pattern that holds for any isosceles right triangle. So if we know that two angles or the two sides are the same, right, we know we have an isosceles right triangle, it's going to have the same pattern. If we call the shortest side x, right, the other leg is also x, and the hypotenuse is x times square root 2. Right, and this is true even if you make it bigger or smaller, the same pattern is going to hold same ratios between the sides. So another example. If we had two sides that were both length 3 in a right triangle, we know it has to be 45, 45, 90. It's not isosceles right triangle. And we know that the hypotenuse would be 3 root 2. Same thing with two congruent angles. We know it's going to be an isosceles triangle. If we know just one of the sides is, let's say, 100, right, that'd make the other side also 100 because that's isosceles, and the hypotenuse would be 100 square root 2. Right, so we're always going to follow the same kind of pattern, x, x, and x root 2 for the isosceles right triangle. Just like for the 30, 60, 90, the 45, 45, 90 isosceles right triangle gives us 3 more trig ratios for 45-degree angles that we don't need a calculator to evaluate. Right, that's not to scale, but let's say this is an isosceles triangle. Either one of these angles would be 45 degrees. Label the sides 1, 1, square root 2. We can go through and find our 3 trig ratios. So looking at the 45-degree angle, sine would be opposite over hypotenuse, would be 1 over square root 2. Same thing with cosine, would be adjacent over hypotenuse is going to be equal. And then for tangent, it would be opposite over adjacent, be 1 over 1. So you can just simplify that, say tangent 45, that's just 1. So again, these are 3 values you'll see 30, 45, and 60-degree angles used a lot on SAT and ACT questions because you don't need a calculator. These are trig values you can do without actually using your calculator. Right, sometimes it will make the problem more simple if you don't use a calculator. You can confuse yourself trying to use a calculator. If it's not in degree mode, you might accidentally put the wrong thing in and get the wrong answer. So whenever you can, try and do this without using the calculator. Also, sometimes you'll see these with the square root 2 with the rationalized denominator. So it's the same thing if you see it written as square root 2 over 2. That's the same thing. These are equal It's just a convention for writing fractions. A lot of time we don't put radicals in the denominator, but either way is fine. I'll accept either answer if this was on a quiz or a test. So that's all for special right triangles. What we're going to do now is talk about inverse trig ratios. So our regular trig ratios, sine, cosine, tangent, our SOHCAHTOA that we talked about yesterday in class, those are the ratio between side lengths. So these represent ratio between lengths in reference to an angle. Right, so regular trig ratios basically represent lengths. Inverse trig ratios represent angles. Inverse trig ratios are angles that have a given ratio between the sides. So they'll have a certain sine, cosine, or tangent ratio. So our notation we have for this for inverse sine, we use a superscript -1 to represent inverse. It doesn't mean raised to the negative first power. That means inverse. So this would be inverse sine. Right? It's also called arc sine. It's written that way sometimes. Same thing for inverse cosine. Also called arc cosine. Right? And then for tangent, it's the same thing. We have inverse tangent. It's also called arctangent. Right, and these are the three inverse trig ratios we'll work with doing these problems. So here's an example, sine inverse 3 over 5. Right, so what this actually means is an angle, right, inverse trig ratios always represent angles. That's an angle with a sine ratio of 3 over 5. Right, so that's what that means in words. You also draw a picture to represent this. Right, using our right triangle trig, if we pick an angle, right, sine ratio would be opposite over hypotenuse, so I can label the opposite side 3, hypotenuse 5. Right, and this is the angle that's sine inverse 3 over 5. It's an angle with a sine ratio of 3 over 5. So what we can do with this inverse trig is use it to find missing pieces of a right triangle without actually knowing the degree measure of an angle. Right, so here's one example, cosine of sine inverse 4 over 5. Same thing again, sine inverse 4 over 5 means an angle with a sine ratio of 4 over 5. Right, if we drew a picture, right, this would be our angle. Sine is opposite over hypotenuse, so it would be 4 over 5. And this question asks to find the cosine of that angle. Right, so in order to do that, I would need the adjacent side. Right, to find the missing side, I'd use Pythagorean theorem. solve. B squared is 9, so the missing side B would be 3. And then we could find the cosine of this angle would be adjacent over hypotenuse, 3 over 5. Right, so just using the definition of the inverse trig ratios, we can use that to find missing pieces of the triangle, set up the triangle, and then find other trig ratios based off of that angle. Same idea for this one. Find sine of inverse tangent 6 over 8. So we set up our right triangle, pick an angle to be our reference. The angle is inverse tangent of 6 over 8, means angle with a tangent ratio of 6 over 8. So ratio of the opposite to the adjacent side, 6 over 8. We want to find the sine of that angle, means we need to find the hypotenuse. Right, so same thing, we'd use Pythagorean theorem. Right, for this one we get that hypotenuse would be 10. So go back to the questions asking us to find the sine ratio, so that's going to be opposite over the hypotenuse, 6 over 10. Alright, so this will be the last thing we're doing with the notes, and then we'll be working on your practice set after this. It's using this in some application problems like we did yesterday in class. Instead of finding side lengths or finding heights, we're going to actually be finding the angles of elevation and depression. So this question, we have a 21-meter tall building casts a 25-foot shadow. We want to find the angle of elevation to the sun. So same idea as the problems we did in class yesterday. We're going to start by drawing a picture. So I've got a building. Casts a 25-foot shadow, so that's going to be shadow, obviously, on the ground. Right, we know the building's 21 meters tall, and the shadow is 25 meters long. And we're going to determine the angle of elevation to the sun. So the sun would be up here, right, and be forming a shadow. So we have our right triangle right here. So this angle here between the line of sight and the shadow would be our angle of elevation. So to find that, we have to look at which two sides are involved here. So the 21, in reference to that angle, would be the opposite side. The 25 would be the adjacent side. So this is going to be tangent ratio. The tangent for that angle is 21 over 25. So the angle itself, to find it, would be inverse tan 21 over 25. Right, by definition we just went over, right, that's an angle with a tangent ratio of 21 over 25. Right, so for this part, if you don't recognize it from the special right triangles, you put this in your calculator. Again, we're doing things with the trig functions. Make sure, check the mode, make sure it's in the correct mode. It's in degree mode, that's the third one down. Right, to get the inverse trig functions, we hit second, and then our initial trig function. So for inverse tangent, it's second and tangent, and then I put in the tangent ratio for the angle, which is going to be 21 over 25. Right, it gives me back my angle is about 40 degrees. So that's going to be my angle of elevation to the sun. So we're going to do one more problem, and then you'll be working through applications or basic problems and application problems for the rest of the class. You'll have a practice set to work through, so you can practice some of this on your own. The last one, same thing, application problem. We're going to start by trying to draw a picture. So we got a mountain road being planned. It's going to climb 2,640 feet in elevation. Right, and there's a lot of stuff in here. Proposed road is going to be 13 miles long, maintain a constant grade for the entire length. So if you keep reading, it says in order for the road to be efficient for truck drivers, the grade should be no more than 2 degrees. We want to know if that's going to be efficient for the truck driver. So will it be more than 2 degrees or less than 2 degrees for our angle of elevation? So we're going to have to do the same thing to figure this out. So got a big mountain road. It's going to be 13 miles long. It's going to climb 2,640 feet in elevation. That's the same as half a mile. I want to make sure our units match up. So I have miles here, miles here. You could also put 13 miles into feet. You'd be working with bigger numbers, but as long as your units agree, you'll get the correct answer. Right, we want to know what the grade should be. So look, right here is going to be our angle. In reference to that angle, the two sides that are involved here are the opposite side, which is the 0.5, and the hypotenuse, which is the 13 miles. So opposite and hypotenuse forms the sine ratio. So I know the sine of this angle is going to be 0.5 over 13. So to find the angle itself, using inverse trig, it can be sine inverse 0.5 over 13. So again, that's when you can put it on your calculator, make sure it's in degree mode, all that good stuff. Second, and sine will give you inverse sine. Then you just punch in the sine ratio. It's going to be 0.5 over 13. Right, so we have a 2.2 angle of elevation here. Right, so it should be no more than 2 degrees. So the answer for the question is no. Alright, so that's it for the notes. Everything else today is going to be practice. If you need help, you can go back, look over the video, ask me questions in class. If you want to look this up online and find a better video, there's probably a lot of them. You can search for special right triangles for the first part of the notes and inverse trig for the second part of the notes. You'll probably get a lot of good videos, probably a lot better than this one, that can help you out if you're not understanding. Work through the practice problems, try and make sure you can do these problems on your own.